it's always helpful to synchronize between frame numbers and timestamps, right? And that way you can be sure that the data that's coming from one camera subsystem is correlated with the data that came from the other camera subsystem. And this is especially crucial if you're doing across multiple connects to make sure that the data stays in sync. Because as you can imagine, with varying loads on the PC, you can imagine the data will actually get slowly out of sync depending on because Windows and pretty much any OS today is sort of the whole multi-program, multi-threaded architecture. So based on thread priority, based on process priority, so many things can happen. And the other thing also is the data that actually gets pulled from the Connect, the raw cameras in the Connect, is actually done by kernel mode drivers, whereas the data that gets sent into the program from the buffer is actually done using user mode drivers, right? So basically both are running as different threads in different priorities. So many things can get out of sync. So if you're doing anything even remotely complex across coordinating between images and depth and all of that, use frame numbers and timestamps. And it's literally as easy as this. Just call frame number and timestamp. The one other question that I got was about the tilt sensor. And the question was, can we control it manually? And the answer is yes, and let me show you how to do that. Let me bring in a text box. Here's a text box. So a text box allows me to type some value. And I'm going to bring in a button right next door. There's a button. Here's a button. I'm going to grab this button, place it next to the text box. So I'm just going to run it, but I'm going to tell you what I think I want to do. I want to enter a number between -27 and +27, so something like, I don't know, 15 or something, and I want to hit the button, and I want the Connect to go to that angle of view, right? So that's what we want to do. So the way to code that is super straightforward. It's just double-click button to get into the button event handler, and I'm going to say something like connect.NUI camera. And NUI camera basically is a class that denotes the physical Connect device, right? So if you look at what's inside NUI camera, you'll actually see 3 or 4 very important properties. One is elevation angle, which is basically the angle at which Connect is looking, and this is what gets controlled. This is what actually controls the motor, the tilt motor inside the Connect. So for what I want to do right now, I'm just going to say NUI camera dot elevation angles equals text box 1 dot text. I think elevation angle is an integer. What I'm going to get out of text is a string, so I might have to do something like parse, or what was that? How do you parse dot? Something dot parse. Integer dot parse. Oh, sorry. Integer dot parse. Thank you very much. And int 32 dot parse. Parse. There it is. Thanks. And then take this and make it into an int, and boom, that's it. So now it's going to return. Let's see. This returns an int, which takes an int. I think it should be okay. So let me run this, and it's now running. So say I want to look down a little bit, right? So I'm going to say, give me an angle of -10. Push this button, and you see how the Connect moved a little down. And now I can basically say, look at the lights up there. So I can basically say 27 and say push this button, and now it's going to look up and show me the lights up there, right? Here's the thing though. The Connect motor is really, really small, and so if you do this a lot, it'll get overheated and actually literally break, right? So what the way they've sort of made a safety mechanism is if you do this more than 5 times in a minute period or something, it'll throw an exception. So at the risk of breaking my Connect, let me do this and show you. So we did that, right? And now we push it up to 27 again. And see, the whole time that's happening, everything else freezes because at some point it should throw me an exception, but anyway, I don't want to push it too much. But if you see a random exception come out while something like this is happening, the problem is not with your code. The problem is Connect trying to protect itself by preventing too many motor operations at the same time. But basically, yeah. But that's how you set the elevation angle. The one last thing I wanted to mention as we're talking about the movie camera is, actually let me go back in here. Instead of showing the frame numbers and timestamps, let me delete this and let me use that to show you something else. Because we looked at the fact that Connect.NUI camera has a couple other interesting properties. One is elevation angle, obviously, which we use to set the angle. It also has something called unique device name, right? And this basically is the full USB name that Windows gives to Connect. And this is guaranteed to be unique across multiple devices. So let's do this. If I look at what it is, it's a string. So I can basically take it and send it to label1.content equals blah. And now if I run this, you'll actually see, I have to push the button. You'll actually see that this, and it's actually truncating it a little bit. Let me do this. Let me grab label 2, get rid of it, make this really long. Let's run this again. Let's set the angle to 0 so it doesn't have to move. And even now it's truncating, but literally this number right here can be used to identify your Connect. So again, in a case where you're chaining your Connect, sometimes the chain order, if you change, what will happen is the Connect number system inside the Connect's collection will change. So to keep track of which Connect is looking where and coordinate between multiple Connects, we always recommend that you use this string, which is guaranteed to be unique across each Connect in the known universe, right? So each Connect will have a separate USB string and then like a device name that we encourage you to use if you're trying to track multiple Connects at the same time. So that's your NUI camera. And obviously you can go explore NUI camera here as well. If you come into runtime, you see one of the properties exposed is NUI camera, which is of type camera. So if you click on camera, it tells you there's a few properties, elevation angle and unique device name, which is what we explored. There's this method which we'll look at in a second, right after we talk about depth cameras. And then it has basically what is called the elevation maximum and the elevation minimum. You know how I said the limit between up and down is plus 27 degrees to minus 27 degrees? That's basically this right here. If I show what this is, it's actually not showing it now, but it's actually set in the source code right here. So you'll actually see elevation minimum is minus 27, elevation maximum is actually, weirdly enough, it's set in hex. But if you look at what 1B is in hex, we will give me the programmer and give me hex. And now if I say 1B and convert it into decimal, it's actually plus 27, right? So this is how we say plus 27 minus 27. All right, so that was all of the types in the NUI camera. So just let's take 1 minute to really quickly recap everything we've looked at so far. We looked at the way to program your Connect is to use the runtime class. You create a new instance of runtime by choosing one device from your Connect's collection. We saw that the Connect's collection obviously exposes something called, it's a collection, so it exposes a count property that tells you how many Connects you have. And the way you initialize is by choosing one index. In this case, I chose index 0 because I only have one Connect. And once you do that, you basically call the initialize method. And once you create the initialize method, the drivers are set up, everything is set up, so you can actually start using the subsystems inside the Connect. What we did was we started using the video stream, which is the video subsystem. And video stream is of type image stream, so let's go into image stream. In image stream, you see that there's 3 methods. What we did was we basically explored the use of using open, right? which opens up the video subsystem that starts getting the data inside, stores it into the buffer, which is what the pool size here is. And then we talked about accessing the data using the get next frame method call. This is a manual polling way of accessing data from the raw stream. So regardless of how you get the data, once the data comes in, it has these properties, right? It basically has a height, it has a width, it has a resolution and all of that. And it basically sends the raw data in whatever format you request. Now you can take the data and do whatever you want to do with it. You can basically, like we did, you can do something like make it into a bitmap source and show it on the screen. But you could imagine doing something else. You could imagine just taking the raw data and storing it to disk. And instead of making it into a bitmap source, you probably perhaps can make it into a MPG format or WMV format and make a movie of it. Or you can take the data and instead of showing it on the screen, put it on a network socket, and you've just created yourself a video chat application, right? What the data will do is traverse across the network stream and show up on the other end. So literally, it's limitless what you can do at this point. Literally, you have the data from the video stream, is what I'm talking about. We also looked at the option of, instead of using the polling method with get next frame, we looked at the option of hooking onto one of these methods, in our case, the video frame ready event, which basically allows you to automatically get called every time a frame is ready in the buffer to be read. And the best part is when you do this, you don't even have to call the get next frame manually. The data, the image frame data from the buffer is automatically copied and sent to your event handler, where you can just basically take it and consume it any way you want. So, which is the current approach that we're using right now. When the video frame ready gets called, this event argument E has this property called image frame that has the relevant data already retrieved from the buffer. We also looked at a couple of properties in image stream, like not the image stream properties, but we looked at a couple of properties in where was that? Yeah, we looked at exactly. We looked at frame number and the timestamp properties, and we looked at a couple of properties in the NUI camera class, which basically represents the hardware connect device. We looked at the elevation angle, how you can set that to make the camera move, and we looked at how you can retrieve the unique device ID from your connect. So I know we've only looked at video camera yet. We haven't looked at depth. We haven't looked at skeleton. But the point I'm trying to make is if you understand where we are so far, you basically get connect program. Because I'm going to show you how to do depth and how to do skeleton right after this. But you're going to see that the process is exactly the same. The code we're going to write is going to be exactly the same, right? So this is sort of the fundamental building block of sort of the sort of a way to think about accessing data from the connect. Right? Any questions so far? Okay, cool. How are we doing on time? How much more time do we have? 1 hour, perfect. Okay. So why don't we do this? The next thing let's do is let's start working with depth data. So instead of having just one image, let me actually forget about images for a second. Let me come back into our source code. Let me show you how to start using depth data, because again, that's one of the coolest aspects of the Connect. But before I do that, let me show you a couple of slides, because I think it's going to help us. Okay, so we left off here. We looked at the different namespaces in Reflector. We saw that runtime is the most important class. Okay, this is important. We saw the different streams that are possible from the Connect. We looked at the color stream. The default resolution is 640 x 480, but it can also be 1280 by 1024 if you want. Now, I just got a quick comment to make here. If you do 640 by 480, your frame rate is going to be 30 hertz, right? 30 frames per second. If you do 1280 by 1024, your frame rate will drop to anywhere from 10 to 12 frames per second, right? So that's something you have to keep in mind. You're gonna be paying a price for getting a higher quality frame rate. If all you're doing is something like a chat application, it really doesn't matter. 10 to 12 frames is still pretty good. But if you're doing something with near real-time video, then you probably need 30 frames a second and so 640, 480 is the range. Similarly, depth stream is a 320 by 240 resolution. I also said that you can actually pull an 80 by 60 frame. It's a much lower resolution, but if you're tracking, say, only one human or something like that, that could be sufficient too. The reason you would probably do 80 by 60 and not 320 by 240 is if you feel that you're running an application and it's on a really slow PC and your bandwidth is really constrained and all of that, and your application is not working at all properly, then try 80 by 60, right? I mean, it might make things a little faster and see if it works for you. But basically, the default resolution of a depth stream is 320 by 240. And the key thing I want to point is, even though it seems like it is returning an image, it's actually not returning an image. The depth camera does take what it sees in front of it and it breaks it into a 320 by 240 image, but the data that's coming in at each pixel is not RGB values, it is not grayscale values, it is the distance between the camera and the device it sees. And I think I called it out in the next slide, but there's a very specific range that the Kinect can see. For instance, the Kinect cannot see to the end of this, to the back of this room, right? The Kinect cannot see something that's too close to it either. The Kinect can only see distances between 850 millimeters, which is almost like 1 meter away, to about 4 meters, right? To about 4,000 millimeters. So we'll look at that in the next couple of slides. We saw how the Kinect can actually return frame numbers, timestamps, and the tilt sensor data, and we'll look at the audio stuff in the next few slides. So we looked at RGB, again, and this is important. We looked at how you can access data from the camera using the eventing model. When you call the, when the event fires, it'll pass you an image frame, and inside the image frame, you'll basically get all of these different components, right? The frame number, the timestamp, and all of that. But the most important property there is obviously this field called image, and inside the image field, you get the actual raw data in this field called bits, right? We saw all of this. So this is just more detail. It's just 32 bits per pixel stored in the BGR32 format, you know, blue channel, green channel, red channel, empty channel, all taking up 32 bits per pixel. And the way the array is set up is it starts at 0, 0, top left, moves left to right, left to right, left to right, and so on and so forth. That is why you need the stride to indicate how many bytes are in one row. So right after that row, you start reading the data and you start reading the next row and so on. We talked about stride just now. So we saw the demo of the RGB camera as well. Now let's actually talk about the depth camera. The depth camera does, there's two ways that Kinect allows you to use the depth camera. One, it gives you the raw data from the depth camera. Or the second way is it can give you slightly processed data from the depth camera. And by slightly processed, what I'm talking is it will do something called player segmentation. So on the left, you basically see, or actually let's look at this, let's look at a scene where, you know, it's seeing a 3D scene. There's a person standing in front of it. By just getting the raw data back, it'll send you the raw distances across each pixel in the 320 by 240 image that it's creating. But when you turn on player segmentation, what it also does is it applies the object recognition algorithm and figures out if in the frame that it is seeing, it can identify a human character. And the way it identifies a human character is to be able to see, in fact, this is a good estimation, it should be able to see the head all the way to at least the beginning of the knees. If it can see the head to knee, it can identify a person as a player and not just return the raw distance, it will also return if on that pixel it thinks that there is a player present or not. So at this point, it is still not doing skeletal tracking. It's still not giving you the head position, the shoulder joint position, the hand position, and all that. It just tells you at this location, I think there's a human being, or at this location, I don't think there's a human being, right? What is a fantastic application of this? Green screen is a great application of this. Green screen is obviously a setup where you set up a player in front of originally a green screen, and then you record somebody doing something, and then later in post-production, instead of the green screen, you actually put the scenery behind, right? In the movies where you see somebody's driving a car really fast and all that, they maybe are not. They're just sitting around in front of a green screen, and then you substitute the background much later. This is a very low-cost way to simulate a green screen because of player segmentation, which we'll look at in the demo in a second. So the way to access depth data is exactly the same as the way to access video data, right? You hook into the event, it'll return an image frame, and all of the data is going to be inside the image field of the image frame, and all of the depth data is still going to be inside bits, right? So it's exactly the same as before, which we'll see in a second. But the important distinction here is that instead of 640, 480, the default is 320 to 40. And depending on if you use just the raw depth data, if you ask back for just the raw depth data, or if you ask for depth data and player index, which is player segmentation, if you turn it on, you will get the data in slightly different formats. If you ask for just the raw depth data, your depth is going to be represented in 12 bits, right? It's going to take 12 bits to represent your depth, and in the 16-bit structure that gets sent back, the lowermost 12 bits are going to be encoded with the depth data. The uppermost 4 bits are going to be blank, are going to be 0, right? So, which is what I call that right here. Uppermost 4 bits are unused, the lower 4 bits are, or the lower 12 bits are the depth data. And like we said, the visible range, or the depth range for a Kinect is between 800 millimeters, which is almost 1 meter, to about 4 meters, 4,000 millimeters. So that is the range, and that's what gets encoded in the byte. Quick question, does anybody know why depth is represented in 12 bits? Anybody? Right. Now, if the range of the Kinect were different, if instead of it being between 800 to 4,000, say had it been between 800 to 8,000, would we have needed more than 12 bits? Yes, right? Because 12, and this is a fantastic trivia question. In 12 bits, you can represent a number up to 2 power 12, which is 4K, right? Which is 4096. And as it so happens, since Kinect can only look up to 4 meters, up to 4,000, 12 bits is exactly enough to represent this range. In fact, even 11 bits would not have been enough, even if you consider the fact that it can only go from 800 to 4,000. So effectively, it can encode 3,200 millimeters. You still need 12 bits to encode 3,200, because 11 bits were only encoded, I don't know, 2K, 2048. So that's the reason for 12 bits, and it's always a fun question. But literally that's what happens. You get a raw 12-bit image. Instead of getting RGB image like before, red, green, and blue channels, you get a 12-bit depth information. It's just going to return a number which is going to be between 800 and 4,000 across 12 bits. Now here's a really interesting part. If you turn on player segmentation, which basically means if you say, Kinect, I want you to identify human characters in the depth frame, then it will use 12 bits as before for the depth data, right? It will return the exact same depth data as before, but it will also return player mask in 3 bits. So a Kinect can recognize up to 6 people standing in front of it, right? So if 6 people line up, so if 10 people line up before a Kinect, it can identify up to 6 human characters in a frame, right? So the values for the segmentation mask will be between 0 and 6. If it's 0, it means that it doesn't see any humans in the frame. 1 means 1 human, 2 means 2 humans, and so on, up to a maximum of 6. So from 0 through 6, that's like 7 numbers right there. So we use 3 bits, because 3 bits can encode up to 8, right? 2.3 is 8. So we use 3 bits to denote how many characters that are on the scene, and that now becomes the lower 3 bits, and then the next 12 bits are your depth, and then the uppermost last bit, the 16th bit from the right, is unused. Does that make sense? So when you use depth data, you have to be careful if you're using the use depth option, or if you're using the use depth and player index option, because accordingly, the content encoding system will change. And here's another interesting thing. All of these values are stored in little endian format. Everybody understands little endian, right? Little endian being, if a number is broken across multiple bytes, then let me tell you with an example. Say I want to represent, for those of you that don't know little endian, say I want to represent the number 12, right? The way I would write it is I would write the 1 first, and then I would write the 2 first, because as humans, we intuitively follow the big endian format, right? Whatever is the bigger number, we end up writing it first, right? So when I say 12,